gonna wait until about 5 after, so, geez, 5 minutes into this video, um, before I start diving into the content. Just waiting for people to join, but I'm back on my normal setup, so hopefully the screen's a little better. Hopefully my mic's a little better, and hopefully that beeping behind me stops. Eh, Copying and pasting Python, I swear, like never works. So for the lab, I didn't find the additional resource you mentioned, lab instructions. Like these two? Oh yeah, there's that delay. Uh, um, the lab post in Canvas. Yeah, I was gonna do, I still hate that there's a delay on this. I was gonna do the normal kind of page thing, and then I just linked them in here. So I didn't end up making a page, since I had the announcement already, and then these two links. I thought that was enough. But the ones I refer to in the instructions are, basically these two to go over kind of what classes and objects are. It's like definitely a deep dive. Like I would have liked to have a whole week on this notion of objects and classes, maybe even two actually. Um, but there's not enough time because it's only 6 weeks. And in fact, there actually was a part on objects and classes when I thought this was an 8 week course. Um, so I thought the best way would be to kind of give a high level exposure of it in a lab, something I can walk over now so everyone can have the answers. And at least have exposure so then if you come across similar code like this, it's like, oh, class, and then, making an instance of the class that you're at least kind of familiar with it, you're like, oh, that's making an object. So I know whatever's being called on that is probably like contained in this class and I can see the code. That's kind of what I wanted the takeaway to be. Um, for this lab. So I think a lot of it, like, you interact with this node class and code, but you technically don't write any of it, but it's still like the logic and understanding it definitely made this lab challenging. So to give some exposure to like the syntax, like, hey, what is even a class right here, right? And what is this object you're talking about? And how can you just make something of this class and start calling this on these kind of functions on it? So I was kind of scouring the internet for some good sources, and I thought these two were pretty good. Um, but I mean, maybe not. I mean, you can definitely give if you thought they were good or if you thought they were trash. I definitely want to know. But I'll also kind of go over the concepts now and answer any questions. But definitely, also, I hope, right? I think I put this on there that I just wanted everyone to kind of try. Um, yeah, because I know it'll be challenging. So like, if you're spending like 4 hours on this and like you still don't get it, I wanted you just kind of just like submit what you have. Like if you looked at the resources and you type some code and you couldn't get it to exactly line up with like what the test function should output, but you still submitted something to show you like tried, then that's totally fine for this lab in particular, because it was kind of like a deep dive, uh, like kind of drinking from the fire hose. Like, oh, here's classes and objects. Also, go ahead and complete two functions for this object, uh, and dive in for this concept that we also just learned, right, with linked list. But yeah, so I'll go in. So I'm gonna assume everyone did the OLI module. I was pretty brief this week about linked list, so I'm gonna assume everyone kind of has like a high level overview of linked list, um, which it's right here. Basically, you have a node or an element that has data in it, and why would you use a linked list in Python? It seems to be a bit clunky. Yeah, so linked list. There's also something called a doubly linked list, which like links back. So if you can see, there's like this head node, right, and it links to another node, another node. And then there's something called a doubly linked list, which is the exact same, but it also links back. So it's not like every node knows the next node, but every node also knows the previous node. And so then it kind of preserves this like order. So you could use it for, well, that's a good example. I guess something that you'd want to preserve like order on in a way, like in a sequence. I mean, we could also just, you know, realistic linked list applications. Look at this, Cora. Yeah, I would ignore. I mean, definitely like there's some like more hardware low level memory stuff. I think like history, like an undo stack in a way, is kind of useful. But then there's also this data structure thing called like a stack, which is generally used for it. But you could use a linked list for like an undo, like in a paint program. A real life example is a train. I don't know if I mean I guess, but I wouldn't really say. I think too with linked lists, so what a lot of programming courses unfortunately do are like, oh, here's, I mean, there's probably like 25 data structures that are kind of taught throughout like an undergrad CS degree in general, um, that do different things in a way, but they all have a similarity, like something similar to them, right? They're like data structures, they store data. I think linked lists are good because they kind of build off arrays and like, which are like basically lists. Um, in a way that also gets you to think about how there's different ways to kind of like store this data. Um, and so again, it's like for the computational thinking aspect mostly, but also for this whole concept of data structures, which it's like, oh, it's almost like a rabbit hole, unfortunately. But yeah, I think I do. I guess if I had to say, I think that you're like an um, undo stack like that. For like paint programs and all would be a decent example. I wouldn't count a real life train as an example. um, but another part of this too was like, hey, there's this notion of data structures. There's so many ways that you can order and store data that have different kind of search times and how much like memory and like kind of hardware requirements they take to do operations to them. And so here's exposure to like one that is more like conducive for like intro kind of stuff, but still uh, has this notion of like you need to think of how the data is going to be linked and you can do these different operations on it and having to implement them yourself as opposed to just calling it. Like with lists, there's like you can sort a list, you can search a list and all that, but we never actually had to like make the functions for them. So having to think through that uh, and actually doing it for your own kind of data structure, I think is useful to an extent. I think a lot of CS courses really overdo it. I mean, there's really so many data structures that are barely different from one another, and they're just complex. Even I don't know. I don't want to go on a tangent, but I think linked list is a good one. I do think they have a tiny bit of real world applicability, but I always feel like, I mean, most of the time I'm like literally just using like a list kind of. Um, yeah, no problem. But yeah, you'll find, especially in JavaScript, when I'm doing like prototyping web dev stuff, I do feel like I kind of just, because a lot of that too is like quick and you kind of want to get it done, especially if you're working up to the deadline. So I do find myself kind of like throwing things in like a list in JavaScript, which is like what you'll be using for PUI. Um, or if you want to use Python for that kind of stuff. And then like kind of just knowing the order yourself because you're making it. Like if you had, a drop down list you wanted users to pick from, and then you want to know if you pick the fourth element, do this, then unfortunately I would like, and if I'm working to the deadline or doing something quick, I would probably just like hard code them in a list. And I know, hey, when we do index 3, you need to do this. Um, so lists, I mean, are still probably going to be like your number one most used kind of data structure, right? But so a linked list is kind of similar to a list, right? That it stores data of any type. We can put numbers in there, we can put floats, booleans, strings, whatnot. But what's different about the list is each kind of element or node knows what the next node is in the chain. So that's what these little arrows are. So if you input Alex, and then you have the next node Tom, then Alex knows, hey, I can point to my next node and we can reference stuff on it like get data. And then there's this notion of like the head node, um, which is like the very first element, which I definitely too do feel bad about is that so I was inserting these words, but our insert makes it where the last inserted thing becomes the head, um, which we can walk through, but it's also here real short. So technically end is like the starting head node. So I should have probably made this like, start and then this end, just to be a little congruent, but hopefully it didn't trip y'all up too much. I do apologize for that. Also, I probably should have thrown in this kind of print, which we will go over, but this prints a linked list for you, and it kind of easy to display away. But I was also kind of figuring that like you could do things like, self.head, like get data. And so like that prints fine. And so then I figured if you're like kind of looping through to get the search or the size, that you could just keep printing the like kind of get data of the current node you're at, um, to kind of give you the idea of the structure. But also I probably should have just thrown this in. But then I was like, oh, I don't really want to have to explain these like kind of methods that you can override for each class, but I'm going to do that anyway in this lab session. So retrospectively should have included it. But don't worry, this one's going to be graded super nicely. And again, kind of a crash course intentionally to give you a high level overview. So if you like open this file and didn't even get all of it or didn't even get close to all of it, do not feel bad. It was a lot to throw out for a lab, but that was intentional too. So we'll dive in. So that's kind of a linked list, right? Um, Similar to a list, but this notion of what comes next in the list is kind of stored in the current element or node. And that there's this notion of like the starting one. It's like index 0 basically. So that's what a linked list is all about. We wanted to implement search, which is kind of described here. And we wanted to do size, which is basically traverse, then keeping a count. And then you'll also use similar code, probably, I mean, you didn't have to, for search. And so it's kind of similar to what we did last week on where it's like, here's the logic for like recursion kind of stuff, but not the code. Go ahead and implement it in code. So I do want to kind of walk through real fast, like classes and objects and like, hey, what are these underscores? And why is self literally everywhere, but we kind of ignore it um, before diving into this, because I do think it helps. I mean, there's also a possibility without kind of understanding that you could just see how insert's done and then kind of copy the stuff. But it's nice to have an understanding. But hold on real fast. Okay. There's like a smartwatch behind me or something, and it kept beeping. It's driving me crazy. All right, so we talked about a linked list, and in the linked list, there's these elements, which are kind of known as nodes. Um, And what makes them like a node versus like an element is this notion of, hey, what comes next in the list? And having a specific data retrieval thing where elements are normally just like, a string or a boolean or a float in a list. So we need a class for that because we can't just pass in a string, right? We can't just have like string and then like somehow give it this notion of what comes next, right? It just doesn't do that. Like a string can have operations done on it, but a string can't like, you can't add something to it like a get next somehow. That just isn't how it works. So we're gonna need something different. So we do need this node, and so to be able to have these kind of methods of, first we need to like store and like retrieve, like get data. Did I spell retrieve right? Really terrible at typing. I did. So that's like the first thing we want for a node, right? So we pass it Alex. We want to store that value of Alex in the node, and we want to be able to somehow retrieve or get that data and know, hey, this node has the data of Alex in it. So it's like the first kind of thing. Secondly, we need to know which node follows the current one. So we need another arrow part. And that's kind of pretty much it. So you can think of like doing, x equals 55 or 44 as having this, right? Because like we're able to store this in x, we're able to retrieve it, but we can't do this kind of next one. All right. So we're gonna need these two things. So that's kind of what this is. So uh, we'll start off. So there's a thing called classes, and you can make a class of pretty much anything that's not a reserved keyword. I mean, I could do like class something wild, right? And then give it different kind of functions, like whatever I want. Um, you do need this in it basically all the time, which I'll dive into in a second. But aside from the init, you can make whatever kind of functions you want on it, right? Like call me, there's some self, return 55. So then I can make something of like, x equals something wild. It's going to give me an error because I didn't run it. Then we can do, x, call me, and it'll return 55. So it's literally whatever you want on it, which is kind of similar to when we do things like math seal, which I think is always spelled wrong. There we go. Right? So you can kind of think of it as when we do import that we're importing a class in the background like this. And then in there's something called like, seal. And then it does some rounding magic. So you can kind of think of it like that, right? It's basically what we're doing. We got this thing math that's already imported for us, so when we do import. So you can assume someone did like a little math call like that, and then they're just calling one of these many functions on it. So we can have as many functions as we want. And what's kind of nifty is there's a certain, I think there's like 5 functions that are kind of all classes can have. And that's kind of what gets at these like underscore things. So like it's very common when you have a class. Oh, and so Python's like an object-oriented language. So classes are basically like objects. Like if you have a class here, then you can make an instance of it, which is known as an object. So like when I do this, oh, do I have it running? Nice. Um, that's saying, so this is like making an object. So this is, hey, I know there's this node class right here. I know it contains all these kind of functions, but since I have this right here, class node, it's going to make an instance of the class known as an object. And then on the object, which is going to be equal to x, I'm able to call all these different functions on it. And to get to this point of this weird init, classes have these different functions that can be overridden on them. I think there's 5, like delete, length, init, and string. Maybe something else. But what init does, it's like the initialization of it. So it's like when I'm making my object, right? So I do node. Generally, when you have a class or an object, you're gonna want to pass some like initial data into it because you don't want to just do like get node and then have to call like x, like add some data, x, I don't know, add something else. Keep doing that. So they give you kind of by default this notion of, hey, we're going to assume that most classes will want an initialization function where you can pass in like kind of whatever you want. So you can do it in data, you can do like name, keep adding to these, you can just go like on and on. And that's basically saying, hey, when I'm first kind of initializing my object, go ahead and pass it some data to set up our object as like the initial state. Like, what do we want to do for this? And so what's great about nodes is our initial data is going to be basically whatever we want the data of the node to be, kind of like an element, right? So this could be a string, this could be a number or whatever, and it should also kind of autocomplete, I think. Yeah, init data. And so that's what init is saying. It's you can kind of think of it basically as being like this too. Um, but instead of having to do like node.init, right? It just kind of comes with it because that's just a Python syntax thing where it says, hey, if you're gonna do these two underscores and then init or string or length or delete, like delete, length, stuff like that, um, then we'll know it's kind of like a property of this class. Um, so that's why also for linked list has init too, and you're able to pass something in. So, if we made another class of whatever name and we had an init here, then we're able to directly do the open parentheses, put something in, close parentheses on it, if that makes sense. So that's kind of what the weird underscore notation is getting at. It's saying, hey, in Python, we're assuming these classes, which are going to be objects, will want some initial kind of data loaded into them. So we're going to have it where we're just going to assume that these classes will need an init function in there. And so, hey, if you throw a double underscore init, double underscore, we'll go ahead and kind of like bake that into your class to help you with initialization. That's what that's doing. And kind of relatedly, if you see self everywhere, that is like another Python thing that like Java and some of the other big languages do, but they don't like make it explicit to you. Um, so like in a lot of them, like you can just do this, right? You won't have to have self, like if you're using Java or another programming language. But I was actually just reading a blog post on this to know like why is it still like that? Because I could see it maybe when the language first came out a long, long time ago, but now I feel like it's more of the trend to just not have that. But the creator does want it like that still. But hey, Python's super, super popular, so I guess it's working. But what that's saying is self is basically passing in an instance of the object. So in Python, these functions aren't specific to the given instance of the object. They're specific to the class. So like, I feel like this is getting too down the rabbit hole, but so if we do that and I call get data, so when I call get data on X, it's like the same get data that I would call Y. And so to know what data I need to return, it has to pass in this like implicit self that doesn't actually get viewed by us, but like behind the scenes in the program, it's saying basically, hey, the instance of this object X, so like right here, pass that as self and then call, data on it. And that's doing it basically behind the scenes. So we don't have to explicitly do like that or something, right? We don't have to repass in the object by having like this first parameter self there, it's basically doing this, right? And so then it's able to like know, hey, we need to get this data of the object X that we're passing in. But since we're calling it on it, and we just have self as a parameter, it knows to basically implicitly kind of pass that in and to not show it to us, which is kind of rabbit holey. Um, but hopefully that's so you don't really have to worry about it too much. Just anytime you'd make a function, just go ahead and throw self in there. Um, Although I'm pretty sure in Python, if you do something like, I don't know, like return 5, then you don't have to. because we're not referencing any kind of properties of the object. Like we're always returning 5. So if X calls it or Y calls it, it doesn't matter because it's not specific to the object. But yeah, probably just more confusing than it's worth. But that's what self is, which is also confusing because then every other time we've seen a parameter, it's like, oh, you need to pass something in. But in these cases, you don't. But hopefully, if you did like that, you'd see that it doesn't want anything. But set next definitely does. See, and it's just new next, so it kind of avoids self. So you can kind of ignore that. But so that's what getData is doing. It just passes in basically the instance of the object behind the scenes and then says, hey, what was the data? And that's something we would assign when we initialize it right here. Same thing with setting the data. If we do want to update it, then we can set it to new value. And now we have new value. By default, this is the notion of next. So the two properties, data, which is this first one, and then second one, knowing what the next node is. By default, it's none. And so calling get next when you first initialize returns none. See, nothing. And then to set it, you would set it to another node. So, sets the next node of the given node. So then, X, set next, I could pass in Y. And so now in our chain, we have yeah. Now technically in this chain, we have this. And so that's kind of the whole node class. Also, if I do print X, it's, this kind of like cryptic data storage of it. And that's because, we did a init, which is one of the kind of 5 methods you can override for classes and objects. Very relatedly is this __ str for string, which is basically the same kind of thing as init. It's like, hey, we're going to assume you're going to want to print or represent your object as a string in some fashion. So you can, print it out for debugging. So you could write it to a file. So you could manipulate it in some way. And so what string is saying is how should you display this current object as like a string? So if you don't have that, like node doesn't have that. So then when I try to print X, it just calls like this default thing. But then when I make a linked list, since I do have this string thing that I added, it'll actually print out the linked list as a string for me, which I did not include in the file. And I probably should have retrospectively. But we'll once we start completing these codes, I'll add a little print statement here and we can check it out, what it looks like. So yeah, so a linked list is a series of these nodes that we just went over this node class, right? So linked list is kind of like a normal list, but it contains these nodes. So it's just kind of like a wrapper for these series of nodes, which would be called a linked list. So when we initialize it, basically when we do L equals linked list, we can pass it in a head node, or if we don't, then it'll be default to none. So what this little bit's saying, equal to none, is hey, we expect a parameter, which is the head, which will correspond to the head node. But if nothing is passed in, then we'll just assume it's none. So it gives you like the option. So we could have just done this, since we're always going to pass it in something, at least for test. Then it will kind of enforce us to do something, like we'll have to pass in a node of some sort. But when we have this equals to none and saying, hey, we really want you to pass in a parameter that equals to head, but if you don't, we're just going to assume you passed in none. So then we'll set self.head to none. But again, since that was the thing we didn't cover, probably should have just had it like that, but now we know. Yeah, so the init of a linked list wants a node to be passed in that's going to correspond to the head node, and that's it. That's all init wants. Insert, so it inserts so this insert is for data that will create a new node, as you can see here. So we don't have to pass in a node for insert into our linked list. We can just pass the data we want, and then it'll go ahead and create a new node that has that kind of data and add it to our linked list. And this kind of insert adds it to the head. So as you see here, it makes a new node of the data. So when we call insert, so it's basically saying, let's just do this again. 50, let's assume we pass in 50 for insert. So it's saying, hey, new node equals this node with 50. It currently has no next by default, as we know. So then saying, all right, we'll make the next node this head node. And so now we don't have a head node, right? Or I mean, we do have a head node still, but we need to actually fix the kind of pointer to it. So now let's make this new node we just inserted the head node. So kind of intuitively, you may think that a linked list would want to add to the very end of the list. And that's the case. There's kind of three main inserts you can do for a linked list. You can insert at the head, you can insert at the tail, very end of the linked list, and you can insert at a given position. So those are kind of the three usual insert cases. But the reason that our insert is at the head is because these other two kind of require you to traverse the list, which would have made size and search, I think, a little too easy, because then you could just like copy and paste the traversal code. And then for size, you could just add a single variable count to it. And then for search, you could just do an if statement. Um, so I was like, yeah, let's have insert just be the case where it's at the head. But then again, that makes this kind of confusing because in the most recently added node is the head, which in our case is the word end. So then technically, the list goes like this, which we'll see when we print it. So start is truly not the start, except I guess at this point when it's like the only node. So that's what insert's doing. Passing in some data, Boolean, a string, a float, whatever, making a new node for it, saying, hey, the head and everything the head already links to is going to be the next node for this. And now let's make this newly inserted node the head. So it adds it to the start. Now we need the size. So, for lists, we just do length, list. But we can't really do that here. So we want to know the size of the linked list, so how many nodes it contains. So one way to do that would be to just kind of iterate through each node and keep a count variable that we increment. But to increment or to kind of iterate through a linked list, we can't just like index into it. But thankfully, each node contains the notion of what node follows it. So we'd probably want to make use of get next. So let's start writing some code. Delete that comment. So we're gonna have to start with a node. All right. And then we're gonna want to kind of get that node to get next and keep going and going until we run out of nodes. So self.head is a pretty good place to start since it's like the starting node of our linked list. And it's the case that, maybe we don't even have a head. Maybe the linked list was initialized with nothing, or maybe it just has one node. But either way, always nice to start at the kind of head of the linked list because that's the start. Already kind of have this count variable here for us, which is going to correspond to the size. So I guess I'll set it up so we don't get an error. Now I'm going to want to start looping through this list. I know I'll need to do something like get next for that node and kind of keep looping over it until we don't have a next. And if we don't have a next node, remember it's none. So I'm not going to want to do like a for, so I'll do a while. And this is also kind of a point that could potentially be troubling. So while the node I'm currently at, which in this case is self-head, is not equal to none, let's go ahead and do some stuff. Because again, we could have a linked list that was created and like maybe we didn't even pass in something to the head, so it is none. So then when I do current equals self.head, it's equal to none. So technically we wouldn't want to increment count at that point because we could have an empty linked list. So in here, I'll definitely want to do something with incrementing the count, knowing at least we have self.head. I guess it's fine if it goes first, doesn't really matter. And then I'll want to advance to the next node, right? So current should equal current.getNext. So this says, hey, we're at the head node. So I guess in this little example we have on this YouTube vid, it's going to be Alex. While current is not equal to none, so has value, it has this instance of this node class. It's not none. Let's go ahead and increment count because we have a node, and let's get the next node in this chain if there is one, and assign it to current, and then we'll go back up here and do the check again. So then it goes Alex, Tom, Karen, Mark, and then from Mark, it says, hey, while current not equal to none, well, it's not because we have this node with the value of Mark. So we're good. Increment count again. Current equals, current.getNext. So then when we try to do getNext of here, it's just going to return none, right? Because there's nothing else in this chain. And so once we kind of get out of there, the while loop ends, and then we just print the value of count and return it. So that's basically all we need to do for size. We just kind of iterated over it. One thing that could be trippy is if you do like current get next here, but that would leave off kind of the last node, right? Because then if we got to Mark and it's like, well, current get next not equal to none, that's not the case because Mark's next node is none. So then you wouldn't increment the count here. You just continue. So you want this, and it could also be confusing on like, well, if current.getNext is equal to none, like, will it throw an error? But it won't because, if getNext is equal to none, it's basically like saying, hey, current equals none, which is totally fine. You can assign variables none. There won't be any error or anything like that. And so that's kind of it for size. And just gonna do this for space. So for search, we're going to pass in item, so like corresponding to like a data value, and we're going to want to loop through potentially the linked list and try to compare the kind of value of what we pass into search to all the different node values and see if we hit it or not. And if we do find one, then let's return true because it's contained in the linked list. Otherwise, we'll return false. So there's like this notion of order, but if you pass in order in the sense of like, this node goes to this node goes to this, but it's not like sorted or anything, and there's can be strings, booleans, floats, all that. So it's not like we can do our search better by doing some kind of sort. So we probably will want to iterate through each kind of node in our list. So we will probably want to have very similar kind of code to here. We're already doing a basic search here. Or basic traversal of our linked list. So we may make some use of that. But let's go ahead and dive in. So if we are going to want to do that, we'll start with the head node again. And very similarly, we have this found variable, which is going to be true or false. Let's go ahead and initialize it to false because, we haven't found it yet. And I guess we can just dive in, right, to the kind of traversal of it. So while current is not equal to none, but in this case too, we don't just want to keep going to the end of the list and then return whatever. If we find the thing we're searching for at like the first element or the third, and there's like 2,000 items in the list, we're good. We can stop doing this while. So we should probably also do like while not found, right? Because if we do find it and it hits true and it's like the second element, we want to exit this while loop, even if there's 5,000 more elements to search. No sense in kind of continuing the program on. So we don't have a count variable or anything to increment, and this will continually loop us on if we do something like this, right? With the current equals current.getNext. But now, before we even do that, we're going to need to do this kind of comparison. So if we want to see if the current node we're at has the same data value as what we passed in, it lends itself kind of nicely to an if statement. So we're getting, current is self.head for this first case, which is a node that we pass in here. And we know nodes have this thing get data, which returns the data that's stored in the node, no matter what it is. Right, so that's what we're calling get data on it. So if it equals the item, then hey, we're good. Let's return true. And then we can increment it in your increment. We can make current got next if we want. You could also throw the else in. It doesn't really matter because if found got hit to true, we would exit regardless. So. And yeah, so I mean that's pretty much the search, right? We're doing the same thing where we're iterating over the list, similarly to here, but each time we're there, add a node, get the data, compare it to what we passed in to see if it matches because we're trying to find it. If it's there, set found to true. We eventually will return found. If it's not there, then we just keep hitting the else, which just continues us on. So found stays false. So we'll return false for the function. And again, if we hit found true, it'll exit us out of the while since we have this here. So no sense in looping over and over. But I mean, again, if you did have that, if you didn't have this part, and you did find it as like the second element in the list, then it's still going to be correct, right? Because we don't set found to false anywhere else. So don't feel bad if you didn't do that. But as you can see, if your linked list was like 2 million items and it was like the first item it was found, then maybe you wouldn't want to continually search over them. It'd be a little time consuming for no reason. So it's good to have that. But yeah, now we should run it and hope it didn't mess any of these up. So I did give a little test function here for this. So you could just call test to kind of see the outputs. 5, true, false, true, true, false. All right, so it looks like we matched up. But also let's do, so I did add this print here, which is also in a Piazza post, I believe, that talks about printing. Or you could just, I guess, type it from pausing this video or whatever. But it should print us out the linked list. Yeah. So what this is doing is, hey, current equals self.head. Eventually the string we print, I'll just initialize it here to be an empty string. And a very similar kind of thing. While current, which is basically saying that, right? We want to get the data from the current node, but we want to cast it to a string because again, this could be like 55 or it could be a Boolean or it could be not a string. So we're going to want to cast it to a string, which is very similar to how for was it tic-tac-toe? Yeah. To how we did the input and we cast it to an int. So that's what this is doing, but to a string. So then we can do a string representation of the data plus this little arrow, and then keep looping through and kind of appending it to this string, which then will yield this. So then that's what our node looks like. So, if we did start get next, you can see there's no node after this little arrow, so there's nothing there. But this allows me to do print because without it, see, it just gives me this. So it is kind of weird too that it's not like print, right? But it's just like, yeah, this kind of Python specific thing where it's like, hey, if you override this string representation method, then we know that when you call something such as print to get the string representation of this object, then we should basically call what's in here to do it. So that's definitely a little annoying, but And I think, so touched on classes as an object, touched on these kind of methods that you override that are pretty Python specific, the kind of use of the magical self word, um, how you can just kind of add any kind of function you want here, whatever you want. I have to do this for print, which is kind of annoying. This notion of linked lists. I think I was gonna make a script for this lab actually to make sure I covered everything, but I feel like I did to some degree. Definitely ask questions if there's any questions there. But again, kind of high level overview of, hey, this is what an object is. This is how you can call functions on an object. Um, Not every, but I would say definitely most programs in the wild, like any kind of software you interact with, which is already likely from like probably Python or Java or C Sharp or C, is going to use this notion of object-oriented programming, which is commonly like that, object-oriented program. Oop. Um, and yeah, that's just the kind of style, like, because you'll have something on a web page like this, like, yeah, I mean, OLI uses object-oriented programming in the back end. So it's just like you'll have, for instance, we're on this page, so there's like a student object probably. Um, and as like we interact with these kind of problems and submit, then it's probably calling a function on this kind of student object that it has, and is like appending my answer to this. Same with these two. So there's three questions on here. So then, they might be something like current student, like, I don't know, submit answer, and then whatever we said, and then maybe also like the question number and then some other information. And then you can like basically print the current student, and then you can get like all the answers that the student has submitted across all these different pages and all these different problems and stuff. Um, but yeah, the two links on the lab I think give kind of better examples. Right, one with like a vehicle and one with an animal maybe, which are like also the two most common ones I think for intro programming. But it's nice because you can have these like you can assign so much values and data and properties and stuff to an object, and then it's still represented by like a single thing like X, which will contain like all this data, and you can call different things to get just the data you need from that object. So it's like super useful programming style that I think you'll dabble in with PUI, um, but I don't know how much you'll need it, especially if you're doing kind of like web prototype stuff. So I just wanted to put it out there in case. Um, yeah. So we got our final homework due Monday. Um, I have lab. What do I need to upload? Lab 3 is graded. Lab 4 is almost graded. I need to upload them though to Canvas. I think I unmuted the quizzes already. Um, yeah, which there wasn't much feedback on the quizzes. The lab's decent amount of feedback, but again, nothing too major. And then just today and tomorrow, I'll be catching up on literally all the homeworks, minus homework 6. So those will come out this weekend. And yeah, you can still use flex days too if you have any and need to work more time on the homework or whatever. Um, I'm not exactly sure when I need to put grades in for the class, but I don't imagine it's, probably by like mid-July, like so a week after the homework's due. But there's only like 5 flex days, right? So, and don't worry too much about grades. I think everyone has a decent grade, and I don't even think I heard back, but I think you just need to like pass the class. So whatever that is, like a 70. But definitely if you hope everyone treated it like it was more of like a graded class because you're definitely going to be using this stuff in the program. And when you're already taking 5 courses that are requiring so much time, trying to come up to speed on this programming stuff would not make you have a very pleasant experience in the program. So part of why we do it now in the summer before you start. But yeah, uh, keep an eye on Piazza all weekend for any kind of homework related questions. There's already been a few, same with the lab. So, if you have any questions, maybe also check Piazza too, in case your question was answered or in case you can answer a question. And we'll put together a little resource sheet that I think might be helpful for PUI. And if you want to dabble in some stuff between when you start the program and I guess when this class ends, which is you have like a full month. Um, but again, also definitely take some nice, you know, relaxation, vacation time before you start the program. It is fairly intensive. It is a lot of courses, a lot of projects. Um, it's a pretty condensed program, especially if you are like, I know when I did the master's, I worked first and then did the master's, and I was kind of like out of school mode. And definitely getting back into that school mode with like 5 pretty intensive courses where I was learning a lot and having to do a lot was kind of a big shocker. So definitely take some vacation time or some non-work time if you can before starting the program. But yeah, that being said, just one more homework. Um, keep an eye out for questions. Grades coming soon. And yeah, let me know if you have any questions or concerns with homework, programming stuff, program questions. I don't know, Pittsburgh stuff, whatever. But yeah, I will see y'all Sunday. Pretty sure. Yeah, Sunday, same time. I'll still be on my normal setup, which is nice. I much prefer it to the laptop. Um, yeah, and I don't think I'll make an announcement when I upload grades, but I'm pretty sure usually it gives you an email anyway that like an assignment was unmuted or something. So you can keep an eye out for that. But again, don't worry too much. And yeah, that's it. See ya.